So, welcome back. Now, in today's lecture, as per my promise, we are going to look at some of the application of Gauss law, choice of the Gaussian surfaces, and how things become easy for us. So, in the first instance, I want to find the electric field due to an infinitely long pencil of charge of uniform lambda. Lambda means the charge, linear charge density. I have defined it for you. Okay. Now, here I take a pencil of charge. Positive charges are placed on, normally we take a metallic wire and we electrify it, and the length is supposed to be infinitely long. It's the theoretical case. Even if the distance at which we are trying to measure the electric field is small as compared to the length of the wire, then also it applies in good approximation. What we do, in the first instance I am taking you through a cumbersome method, a difficult method of calculating the electric field from our knowledge of Coulomb's law. Okay. Later on, I'll apply the Gaussian surface and the Gaussian approximations and Gaussian things to obtain things very easily for you. Whenever we do anything like that, okay, then we want to make our life safer and easier. So what I'm going to take is, we have to find out the electric field at this point P. Okay, some x distance away from the pencil of the charges. Okay, so you can think that this is the pencil of the charges, and this is the distance x from there, and we are trying to find out as to what is the electric field on the circumference of this. Okay, no problem. That we can take as also equal to r, small r. Okay, just to distinguish, I have taken the value x. Now these two elements, dl and dl, on the left and right of the point O, we have taken symmetrically. Okay, so the angle, if it makes theta here, and the angle is theta here, and this is a kind of a isosceles. Okay, both the two sides of which are equal to each other. Now, I take this element, a varying element L, and this is minus L and this is plus L, located from the center which we have taken for the sake of calculation, extends from minus infinity to plus infinity. Okay, now let us see what happens. These two dl elements are of equal length, so that the charge over there is lambda dl and also lambda dl. Okay, the charge is the same. Distance from this point to this point and distance from this point to this point is also the same. Okay, and this will turn out to be equal to L square plus x square under root here also and here also. Okay, so there is no problem. Then I locate the electric field dE. This will be like this, because this is a positive charge, therefore it will be away from the positive charge, and this one also be away from the positive charge. And if I draw a line here parallel to this, then we find that this angle is theta, so this is theta and this is theta, so this is theta. Okay, and I can resolve this dE into two parts. One is d cos of theta and the other is d sin of theta. D cos of theta and d sin of theta, these two cancel out each other and these two add up and they are radially away from this long pencil of charge. So the direction, net direction is away from it, and the value I get 2 dE sine of theta. Now the electric field due to the lambda dl element that we have, the magnitude will be equal to 1 upon 4 pi epsilon naught, the charge lambda dl upon x square plus L square as it is. Okay. And sine of theta will be equal to perpendicular upon the hypotenuse, and that is x upon x square plus L square under root. Okay. So the value 2 dE sine of theta which we get over here, I can put it like this: 1 upon 4 pi epsilon naught lambda x dl upon x square plus L square 3 by 2. Remember, this x is a constant of our choice and L is the value. Okay. Now to find the total electric field at the point P, okay, E total, we will have to integrate it between 0 to infinity, because we take only one side and the other side automatically comes into being. So because we have taken a pair of elements, if we had taken only a single element and then we were doing it, it will be from minus infinity to plus infinity. Anyway, well, this is a bit complex and complicated, and particularly for the students who do not have a mathematics backup, it's difficult. It is. It's not so difficult that I cannot solve it. But when we solve various steps out of this 0 to infinity this dl, then what I find is lambda upon, after many steps, I find this result lambda upon 2 pi epsilon naught x. Okay. Now the same result I will try to obtain by using Gauss law. So now this minus infinity to plus infinity, the pencil of charge which is on a wire, okay, thin wire that we take, and about this we think of a proper Gaussian surface. A Gaussian surface proper is a cylindrical surface which has two faces which are plane on the left hand side and the right hand side, and the radius of this cylinder is equal to r. Okay. Now let us see, let us imagine, take a page from here, and we see that everywhere on this circular cross section of the Gaussian surface we'll get the electric field in a direction which is here is the same as the direction ds. Okay, the area element which is also a vector. So ds element and E element, they are both in the same direction. So E dot ds becomes equal to E ds. And let's come to these anywhere on this surface. Okay, I'm just taking one point there. Then we argue that this left side of the cylinder, this is a plane which is perpendicular to this line. Okay, and therefore E will be in the same direction like here, but ds will now be from right to left like this. How much is the angle between the two of them? 90 degrees, or pi by 2 radians. So E dot ds over here will be equal to 0. There will not be any flux out. Look here, here also on the right hand side, the E is perpendicular to ds vector, and E dot ds will become equal to E ds cos of pi by 2 or 90 degrees, and that will also turn out to be equal to 0. So the total contribution will be equal to 0 plus 0 plus and then the integration has to be carried out for the cylindrical surface, and the cylindrical surface of a sphere is 2 pi r, which is the radius of this multiplied by the L. So it turns out to be equal to 2 pi r L. Okay, 2 pi r into the length of this cylinder, and this cylinder has been taken, the cylindrical surface has been taken as finite surface. So 2 pi r into L, right? 2 pi r into L and multiplied by E. Okay, E dot ds. E dot ds is equal to total charge which has been enclosed, and the total charge enclosed will be equal to lambda into L, and then our friend from the Gauss law, epsilon naught. See, it's like this. And look here, what is going to happen? That L and L will cancel out, which means the length of the cylindrical surface, the Gaussian surface that we are taking, is immaterial, and therefore we'll get our value of E is equal to L and L cancels out, okay, and this is becomes the same as our friend that I told you that the value will be equal to lambda upon 2 pi epsilon naught r x, okay, they are one same thing, but I am distinguishing that so that you understand it properly well. Now look here, in a matter of seconds, by using the beautiful concept of the Gauss law and choosing a Gaussian surface which is of matter to us, which is the beautiful surface, carries certain symmetrical properties, one step is step number 2, and we obtain the value, and we find in both the cases that this is x. Let me write instead of x, if I write r, so what happens? Lambda is a constant, 2 is a constant, pi is a constant, epsilon naught is a constant, the only variable is our friend r. So in this case we can say that the electric field, friends, this is proportional to 1 upon r. So that means as we go away, this side or this side, whatever side, and if we try to find out as to what will be the relation between E and the distance r, then we find that E will be related to r like this. Asymptotically it will become equal to 0, asymptotically it will be equal to 0. So this is the kind of the curve that we have. Y is equal to k 1 upon x, or x y is equal to a constant, so that the area made by these two coordinates will be the same as the area made by any coordinate. So this is the nature of y is proportional to 1 upon x. Y is proportional to 1 upon x. What kind of a proportionality is there? I emphasize, and I tell you again that the proportionality of y to 1 upon x is a direct proportionality. Y is directly proportional to 1 upon x. And my dear friends, there is only one symbol all over the world for proportionality. There is no symbol for inverse proportionality. Okay, so whenever we talk about proportionality is system variation, then we always talk about the direct proportionality. So the next item is, the next case is that of an infinite plane sheet. Okay, infinite plane sheet which I have kept here in the form of a line, but it is actually a plane sheet which extends this side, this side, this side and that side, all sides, okay, to infinity. That means it is a ball of charge. The charge that I am taking just now is a positive charge, so that the electric field will be away from it. Okay. Now what we expect is that the direction of the electric field will be normal to this chadar or sheet of charge. The E cap is like this, and now I have just taken two kinds of Gaussian surfaces. One which is a kind of a rectanguloid, okay. From here to here the distance is r, and from here to here also the distance is r. This is a plane sheet of charge, okay. There is nothing like a metallic this and that I will do later on, okay. Just you have to imagine that this is a chadar or a sheet made up of positive charges with the charge density which is sigma coulombs per meter square. Okay, you understand that? Now let's see how many faces are there. Okay, for this 1, 2, 3, 4, like that. Okay, these faces are plane. They are also kinds of sheets, and they have all their ds vectors normal to their surfaces, which therefore make an angle of 90 degrees. So therefore the flux out from these surfaces over here will be equal to, okay, those surfaces are just like this case. I have taken it here, so how many surfaces I have? 1, 2, 3, 4. These surfaces, the flux out will be equal to 0. But these two surfaces on the sides which we have, they will matter. This surface and also this surface. Okay. So at this surface the area is, let us suppose that the area is capital A. ds vector and E cap, they are both parallel to each other, and therefore E dot ds over there will be equal to EDS. Integrated over the whole thing, it will become equal to EA, like left hand and right hand face both are equal to EA and EA. Rest of the things, enclosures, it will be equal to 0. Okay. The same I can do it. You can do it. No, there is no problem. Let's take a cylindrical surface with two faces which are parallel to the charge sheet. So naturally, in the case of the cylindrical surface that we have, the ds vector and E, they are perpendicular to each other, and therefore the flux out from the rest will be equal to 0. Okay. So I can write in both the cases the total flux out phi as equal to EA plus EA plus 0, big 0. Okay. So this turns out to be equal to 2EA. And using the Gauss law, I can write this, the total charge which is enclosed. Here the charge will be enclosed in a rectangle over here, and here the charge will be enclosed in a circular cross section. There is no problem. So the area here, that's all A, here, and here, that's also equal to B. So therefore, using the Gauss law, Q upon epsilon naught, phi is equal to total charge enclosed Q divided by our friend epsilon naught. That's it. This is the Gauss law. I apply it here. What happens? I find that E is equal to sigma upon 2 epsilon naught. Sigma upon 2 epsilon naught. Okay. Which shows that E of course is a function of sigma. And if the sigma is also known to us, then the value of E will not change at all. It is not a function of R. How much distance away it is, it's not a function of R. Whatever it is at 1 centimeter, the same value will be after 100 kilometers. It's simple. Suppose this sheet which I have, and this gives out the electric field like this. Okay, like polka dots. Okay, polka dots were first of all from Russia and Ukraine, the Soviet Union. Now what is this? These dots. They show the lines of field which are coming out of this sheet. Okay, and the beauty is that the distance from here to here and the distance from here to here, from here to here, here to here, here to here, here to here, this distance is the same. That's what I'm writing. Parallel and equidistant lines of fields. Okay. So the lines of field will come out. They cannot divert from their original path. Else, what is going to happen? That the parallel lines are going to cross each other. Okay? And that crossing is not allowed in the case. That's not in the dharma of electric fields. That's against the dharma of electric fields, and therefore it will be like this. Now, the beauty is that E is not dependent on the value of R, which I can say that E is proportional to R raised to the power of 0. E is proportional to R raised to the power of 0. Okay. Now, next item is a simple item, not very difficult. Electric field due to a thin spherical this thing. Okay. I am not going to do it just now. I will do it in the next lecture. But I am going to tell you the result. There we have, in the first case, today we had a kind of a cylindrical symmetry for the pencil of charge. Okay. Here I will not name the symmetry. But in the case of the spherical shell, okay, the symmetries are, in the case of a point charge, the symmetry is spherical symmetry. Interesting. Very interesting result is that in this case E is proportional to R to the power of 0. This case. In the last case, E is proportional to R raised to the power of 0 plus 1. 0 plus minus 1, which is proportional to R raised to the power of minus 1. In the next case that we are going to talk about, our E will be proportional to 1 upon R square. Okay. So the beauty is that this is the case of a chadar of charge, a sheet of charge. This is the case of a line of charge, and this is the case of a spherical shell of charge. I will draw certain conclusions with the help of these equations, and that will make you remember always as to what happens to our symmetries, the cylindrical symmetry, the spherical symmetry, and this is called reflection symmetry, okay, from a wall. And like that, an extension of this result, sigma upon epsilon naught, sigma upon 2 epsilon naught, etc. That is what we will find in the case of the structure that we call, the structure that you must have been told, and which is called a capacitor, where, look here, why I am giving it to you? I want to emphasize something, that the charges are equal and opposite charges. Total charge inside the capacitor is equal to 0. And the charges, they stay on the inside plates. If this is a plate, friends, and the negative plate is on your side, then all positive charges will reside here, and the charge over here will be equal to 0. Okay? On the negative plate, if this is on this side, all negative charges will exist on this side, and your side there will not be any charges. So no charges reside outside the confines of the capacitor, which by virtue of keeping that distance between the two of them, which is d, having the same area of cross section, area of the capacitor plates A, okay, we get a formula epsilon naught A over D. But this formula has got no beauty. The beauty of the capacitor is that whenever the plates are oppositely charged, there is a lot of energy. Whatever is the energy over here, we'll talk about that energy. And I told you before that the capacitor, just like the spring, okay, is a storage device, like many other things. We'll talk about that shortly tomorrow.